Thank you. First, I would like to thank the organizer for the kind invitation. And today, I'm going to talk about this Escobar theorem for fully nonlinear Yamabe problem. Apparently, this has nothing to do with the topic of this Congress, minimal surface and hyperbolic geometry. But in fact, it has, and I'm going to explain why it has. The way we are going to solve this problem is to, associated to one function, we are going to construct a hypersurface in the hyperbolic space. And then we're going to use technique from constant mean curvature and minimal surface to have to classify this kind of surfaces. Is how hyperbolic geometry is going to play a role in this talk. So the first thing I should mention that this is a joint work with Professor Marcos Petruccio, that is here in the audience. It's not appeared yet, but we hope that it will appear soon, very soon. So let me do an introduction that kindly Professor Ivaldo Nunes made in his talk about the Yamabe problem. So what's the Yamabe problem? Suppose that you have a 3 manifold with dimension bigger than 3, orientable, compact, with no boundary at the beginning. And then you want to find a conformal metric in the conformal class whose scalar curvature is constant. So we can rephrase this problem in a PDE problem in the following way. Find, fixing some constant, that is going to be the scalar curvature of the new conformal metric. Can one find a positive solution to this PDE? From the point of view of PDE, this is a very hard problem because this exponent here. But nevertheless, beginning with the work of Yamabe, I started to study this kind of problem. And then following by Trudinger, Aubin, and finally by Rick Shen, they completely solved this problem. But here, I'm interested in the problem with boundary. What is the problem with boundary? The same problem that Ivaldo said in his talk. It's the following. Suppose that I have a compact manifold now with boundary, with some scalar curvature, some mean curvature of the boundary. Then we would like to find a conformal metric on the conformal class so that the scalar curvature of the new conformal metric is constant and the mean curvature of the boundary is also constant. So again, we can rephrase this problem in a PDE system in the following way. Fixing two constants here. One is going to be the scalar curvature and the other one the mean curvature of the boundary. Can one find a positive solution to this system? So as Ivaldo said in his talk, this problem was studied first by Escobar. Later, Han and Lee did remaining cases that Escobar didn't do. Later, Fernando Marquez solved almost all the remaining cases left by Escobar and Han and Lee. This is for the problem of existence. But here, I'm going to be interested in the problem of classifying the space of solution of the problem. This part. In this paper, this is a really good paper of Escobar, he classified all possible solutions when we know the underlying manifold, when the underlying manifold is the standard Euclidean ball. He proved that if we have a solution to the above problem, where the M is the standard Euclidean ball, and we fix the scalar curvature to be constant and the mean curvature of the boundary to be constant, have to be a geodesic ball of one of the space form. In particular, if we fix the scalar curvature to be 1, this implies that the solution have to be a ball of certain fixing some point for some radius in the standard sphere. That have to be the solution to the problem. The radius of the sphere is going to depend on the constant that we fix for the mean curvature. Bear in mind that in a sphere, take some point P. This is, say, the geodesic ball of radius of center at P of radius R. The mean curvature of this guy goes from plus infinity with the inward orientation to minus infinity with the other orientation. So we can fix any constant here. So, okay, this is the problem that we want to solve, but a more general one. And to generalize this, I would like to remind you what is the shortened tensor and how to relate the shortened tensor of a manifold with this problem. So, as we all know here, given a Riemannian manifold, we can decompose the Riemann curvature tensor into two tensors, the Weyl tensor and the shortened tensor. And the shortened tensor is given by this expression. But the good thing about the shortened tensor is that it encodes how curvature varies by a conformal chain of metric. That's the important thing. And if we have a locally conformally flat manifold, also the Weyl tensor vanishes. So all the geometry is encoded in the shortened tensor. In particular, in our case, if we fix the underlying manifold to be the sphere, it's conformally flat. Therefore, all the information about a conformal chain on the metric is going to be encoded in the shortened tensor of the conformal metric. As a remark, we have to say that the trace of the shortened tensor is nothing but a constant, depending how you normalize, times the scalar curvature. Therefore, we can rephrase the problem as the following. Take a conformal metric on the sphere, and by lambda, these are the eigenvalues of the shortened tensor of the new conformal metric G. And fix the new constant, the new scalar curvature of the problem to be 1. Then we want to find a solution of this problem, a positive solution to this problem, where the sum of the eigenvalues of the new conformal metric is 1, and the mean curvature of the boundary is constant. That is, the trace of the shortened tensor is 1, and the mean curvature of the metric, of the new conformal metric, is constant. For those that are more into geometry than in PDE, we can think on this equation like a constant mean curvature equation. This is like the sum of the principal curvature equal to a constant. So in some sense, this is like a constant mean curvature equation. In fact, we are going to see that this equation we are going to rephrase for hypersurface satisfying some kind of condition on the principal curvature. So we can rewrite the Escobar theorem the following way. The solution to this problem, where this is a conformal metric to the standard one on the sphere, are given by conformal diffeomorphism of the standard sphere. Is that the only solution are both right here, like what it says. But now what we want to do is to generalize this theorem for more general equation. These are fully nonlinear equation. With a fully nonlinear equation. So take a function f from Rn to R and consider the convex cone given by this expression. So we are going to take an open connected component of a positive part of the functional, and we are going to take a function f with respect to the cone gamma that satisfies these 4 conditions. That this is in the cone. This condition, this final condition here and here, this all imply that the equation satisfies the maximum principle. These are the weakest conditions that you can assume for this kind of operator that satisfy the maximum principle. That's all that you have to bear in mind, because we're going to prove this theorem only using the maximum principle. And these 4 conditions here, it looks like kind of funny. It says that in the family of all solutions, you have a dilation of the sphere that is a solution. You at least have one solution to the problem. So our theorem is the following. Suppose that we have an elliptic data, it is functional, and we fix some real constant here. So if we have a solution to this problem, is that the eigenvalue of the shortened tensor are equal to 1 through this elliptic function, and the mean curvature of the boundary is constant, then up to a conformal diffeomorphism of the sphere, the solution has to be the standard one. That is, in the same case, that have to be a ball in the standard Euclidean sphere. Also, this conformal diffeomorphism, we will see through the proof, have to leave invariant the hemisphere that we are working on. So let's go through the proof of this. The proof of this is kind of simple. It's long, but it's simple, very simple. You use geometry from, I don't know, undergrad or something like that. So, okay, the first claim that I have here is that suppose you have such a solution. I want to see that this have to be this standard solution of the problem. So the first thing we're going to do, we're going to dilate the metric in the following way. That the dilated metric satisfies this condition. This has nothing to do because the eigenvalues of the shortened tensor change if you dilate the metric in this way, change in this form. So if this is elliptic, this is going to be elliptic. And now the mean curvature of the boundary is going to change in this way. The shortened tensor is going to be less than 1/2. So since we are working in a relatively compact part of the sphere, we can find T big enough so that the shortened tensor is less than 1/2. And the eigenvalue shortened tensor satisfies this final condition. This follows from these two remarks that I just say, that when you do a conformal chain of dilation of a metric, the eigenvalues of the shortened tensor change in this way. It's going to be decreasing for T big. And the mean curvature of the boundary is going to decrease also. So it's easy to see that from this that we can achieve this condition, it's less than 1/2. And from this and this means that this goes to 1, this part, and this part goes to 0. So we can find some T big enough so that satisfies this condition that I claimed before. So, okay, now we have this metric, this conformal metric. Now we are going to assume, if I find this guy here, I'm going to work now with this metric. I'm going to assume that, in fact, the shortened tensor of this guy is less than 1/2, and also 1 plus twice is bigger than the absolute value of the hyperbolic tangent. Was this or no? This one. No. This one. Sorry. Okay. So with this new function, there is only a sum of a constant from the new one. We're going to construct a hypersurface. And the hypersurface is explicitly given by this expression here. And the thing is that we're going to see that, this is a very important property, is that the boundary of this surface is contained in equidistant to a totally geodesic hyperplane. Depending, C, remember, is the mean curvature of the boundary. The way to see this is that, okay, given a conformal metric, we are going to construct this hypersurface that is given explicitly by this expression here. You can compute everything. This is the hypersurface. This is the normal along the hypersurface. This is the first fundamental form, and this is the second fundamental form. Here you can see why I'm asking that the shortened tensor is less than 1/2. This implies that this is well defined. It's an immersion, okay? And moreover, one thing that satisfies this hypersurface here is that the hyperbolic Gauss map is the identity. The identity in the following sense. I would like to explain what is the hyperbolic Gauss map. It's nothing but giving a hypersurface, oriented, take a point on your hypersurface, and then the hyperbolic Gauss map is the limit when t goes to plus infinity of the geodesic in the hyperbolic space, starting at the point in your surface with the direction of the minus the normal. So if this is your hypersurface, this is your normal, this is the hyperbolic Gauss map. Okay, goes to the boundary at infinity of the hyperbolic space. There is a sphere. So what implies that the hyperbolic Gauss map is the identity is the following. If I take a point in my hypersurface that is given by some point in the sphere, when upper hemisphere, and I compose with G, then this is equal to the point in the in the boundary and infinity. So, okay, let's see that the hypersurface by condition, with this condition, is well defined. We have a hypersurface. And now we're going to see that the boundary of this hypersurface is contained in an equidistant. How to see that? So, the thing is that we have to rewrite the condition on the mean curvature of the boundary from the PDE point of view. So, suppose that you have this row that has constant mean curvature of the boundary. This implies that the partial derivative with respect to the inward, this is the inward direction, times the exponential of the function is equal to a constant. This is what implies to have constant mean curvature of the boundary. That's a simple computation. So, okay, here you can see the expression. This vector here is this one. So when I aim at the boundary I'm using the upper hemisphere, the x1, n plus 1 coordinate is 0 along the boundary. So implies that the n plus 1 coordinate here is 0. And in this part, we have this condition. So along the boundary, what we have is that this last coordinate is a constant. Is this constant c. So we imply that this vector, be like in the Lorentz-Minkowski space, belongs to this hyperplane. Okay? So, okay, if we take this and we go to the formula for the hypersurface, what it implies is that along the boundary, along any point at the boundary, the hypersurface belongs to the, of course, hyperbolic space and this hyperplane here, where the last coordinate is constant. But this is nothing but an equidistant hypersurface to a totally geodesic. If this is easy to see, I'm going to draw here in the Poincaré-Ball model. This is saying the following. This is the Poincaré-Ball model. This here is the upper hemisphere. This is the boundary. This. So here in the hyperbolic space, we know that we have a totally geodesic hyperplane. This is nothing but to cut with this hyperplane, horizontal hyperplane. So if along the boundary is contained in the hyperbolic space intersection with this hyperplane in the hyperbolic model, implies that this is an equidistant to this surface. So what it says is that the boundary is here. This is an equidistant. A distance, the distance, you can compute the distance explicitly, is the R hyperbolic sinus of the constancy, of the mean curvature. You have two equidistant to this hypersurface, to this total geodesic. This one and this one. Here, another one. Which one is going to depend on the sign of the constant c. I'm going to suppose that it's positive. Nothing to do with that, it's the same. And imply that it's going in this direction here. So, okay, we have a hypersurface. We don't know how is the hypersurface. Even we don't know if this is immersed, embedded, or whatever. This can be some crazy thing here, okay? I don't know how this is, even the boundary. So in particular, one can see that when C is 0 is the minimal case, when the boundary is minimal. In fact, this equidistant is just the totally geodesic we started with. Now we're going to see that, in fact, the hypersurface have to lie in this half space of the equidistant. Let me draw another picture. just for simplicity, I'm going to suppose that this the totally geodesic one, because it's easy. We know that the boundary is here, okay? So we're going to prove that the hypersurface cannot do something like that, okay? How we're going to prove that? Is the following observation. Using the formula that I showed you before, one thing that you can see from the first and the second fundamental form is that the principal curvature of this guy with respect to this orientation here that we have satisfies this condition. These are the eigenvalues of the short-term tensor. So what we have, and we have the other property that this is bigger than this guy, so these are the principal curvature are bigger than this. The hyperbolic tangent of the constant, C. But these, if you do a little computation, are the principal curvature. This is the value of the principal curvature of the equidistant with the upper orientation. Doesn't matter, because I'm taking the absolute value. So let me this is the equidistant here. Probably take this orientation for the equidistant. Okay, this is DC. This is the normal, and this is my surface. So this property say that the principal curvature of any point in my surface, this blue surface sigma, okay, this is this guy, are bigger in absolute value, are bigger than the absolute value of the principal curvature of this equidistant. Bear in mind that when we have this orientation for this equidistant, the principal curvature for this orientation are negative. For the other orientation are positive. This is the convex side, and this is the concave side. Okay, so okay, how to prove this thing? So okay, take with this boundary the equidistant coming in this way. Since this guy is compact, I'm going to find an equidistant far, far, far away that doesn't touch this guy. Okay? So I'm going to decrease the distance from the equidistant to the totally geodesic. Here is my totally geodesic. So I'm going to find a first contact point, say here. And now the claim is that the normal at this point have to point in this direction. Why have to point at this direction? Because the hyperbolic Gauss map takes this point with the normal in the opposite direction. So it should go here or here. If the normal points up, the hyperbolic Gauss map, as we defined, goes to the lower hemisphere. But that's a contradiction with the, how we construct the hypersurface and the property of the hyperbolic Gauss map. So the normal has to point in this direction. But this is a contradiction with the principal curvature. So what implies that if you foliate until you get here, the surface cannot be below this hypersurface, this equidistant. So the picture has to be something like this. Okay. Now, I'm going to see that, in fact, this guy is a capillarity surface in the sense that it makes a constant angle, the intersection of the boundary with this equidistant. And this is, again, a simple computation using the normal. So I think that we have the normal writing in this way. So it would restrict to the boundary, to this boundary here. we have that the normal in the last coordinate is also belonging to this hyperplane, and that implies, using we can compute explicitly the normal along the equidistant, that is this one, for any point, and we can see that the product of the normal along the equidistant times the normal along this hypersurface is equal to a constant. So that means that the angle that it makes is constant along all the points. Okay, so now we're going to see that it's embedded. I don't know that the surface is embedded or not, but I know that the angle is the same here and here. Okay? How to prove that this guy is embedded? The first thing is easy to see that the boundary is embedded in this equidistant. This equidistant is a hyperbolic space whose sectional curvature depend on the principal curvature and given in this way. This is less than 1. So it's isometrically to a hyperbolic space. But the thing is that the principal curvature of this guy are bigger than the principal curvature of the equidistant. And we can also compute the normal. The normal of the boundary in the equidistant is in this way. So we can compute the second fundamental form of the boundary in the equidistant. It's given by this, and this is positive by this condition. So we have a compact surface in a hyperbolic space, which is convex. So the famous theorem of Dockarman and Werner say that have to be embedded. So, okay, we have something that we begin with is embedded, the boundary. And by the previous, we know that no other point, other interior point of the surface touch this guy. So we can translate this equidistant, say, here, so that the intersection is transverse and have to be embedded. So we are going to keep on going. But the thing is the following. In general, one can see the following. For any transverse intersection of equidistant, a translation of this equidistant with the hypersurface have to be convex using this simple computation. So again, since the surface is compact, the intersection have to be compact. Using this computation have to be convex and compact in a hyperbolic space. Therefore, using again the Dockarman-Werner theorem, have to be embedded. So using an argument that Harold and Jose Antonio and me developed in other paper, we can see that at the beginning, this intersection have to be compact and embedded, keep on going, moving this equidistant along translation. And we can see that all the intersections have to be only one component, because suppose that, for example, here, suppose at some point you have two components. Since the principal curvature of this guy are bigger, excessively bigger than the principal curvature of your equidistant, the intersection have to be transverse or only one point. You cannot have a line, otherwise you will have some direction where the second fundamental form is equal to the value. So it's a contradiction. So, okay, suppose you have this, and at some point, since this is a homotopy sphere, half sphere, you have to, these two components have to join in one. But this means that you have some principal curvature going in one side of the equidistant and the other in the other side of the equidistant, which contradicts the fact that the principal curvature all point in the other direction. So at each level, you only have one connected component, and if it's transverse, have to be embedded. And you have to end this surface because it's compact. So the last one, the last cut, have to be only one point. So it implies that the surface has to be something like this, okay? With the orientation pointing in this way. Okay, so what we have is, say, something like that. This is my sigma. Okay, I have time. So far it's okay? Any doubt? Okay. So remember that we begin with an elliptic problem. We want to see that this hypersurface also is elliptic in the sense that satisfies the maximum principle. So we can see that this sigma satisfies this elliptic relationship, this W. We're going to see that this is elliptic. And moreover, as we saw, the angle that it makes with the equidistant is constant. So another way to say this is a capillary surface. And the angle is this one that we computed before. How to see that this satisfies this elliptic equation? So the only thing is that we have to compose the original because we know how to relate the principal curvature with the shortened tensor, with the eigenvalue shortened tensor. So if we define the functional depending on the principal curvature in this way, using this transformation, we can see that this data now is elliptic. Elliptic in the following way. We have this function, this W star is a connected component of this part here, of the positive part of the functional, and satisfy these three finite conditions, let's say above, that implies that satisfy the maximum principle. The hypersurface satisfies the maximum principle. And the fourth condition that I said before on the functional f, saying that you have dilation of the sphere, which is a solution, you have at least one solution, translate into this condition. It means that in the family of surfaces satisfying this condition, you have a totally umbilical sphere. That's what it means, this condition. This is how you rephrase the fourth condition for the elliptic functional f. So, okay. Now that we know that this guy is elliptic, we're going to see that it's rotationally symmetric. And this is, for those more familiar with hypersurface theory, this is only applying the Alexandrov reflection method. How to do this? The way is the following. You have this totally geodesic. Take a geodesic in this totally geodesic. So in this, we have one-dimensional guide, so it's this geodesic. And take the foliation of totally geodesic hyperplane orthogonal to this one. So say this. This foliation leave invariant this equidistant. Okay? So we can, if we go far away here, close to this point at infinity, we can see that this totally geodesic hyperplane doesn't touch my hypersurface because it's compact. So I can approach until the first contact point. And now I'm going to start to reflect the surface. I'm going to find some hyperplane so that when I reflect, it's going to have a first contact point, interior or boundary. So applying the maximum principle, that will say that for this direction, I will have a plane of symmetry. But I can do this in any direction. So it's standard in the theory that when you have this, that implies that this hypersurface is rotationally symmetric. So what we have is something like this. This is the same angle here. Bear in mind that the first contact point can be at the boundary, but that's not the condition that the angle is the same along the boundary. That's say that when you touch at some point at the boundary, you can apply the maximum principle there. So that's important. That's the very important condition that the boundary makes a constant angle along the equidistant. So summarizing what we had, the following. Suppose that we have a solution, rho, of this problem, and we do this dilatation that I explained at the beginning. So what we have is a hypersurface in the hyperbolic space with boundary in this equidistant, which is rotationally symmetric, and is embedded, and is contained in this part. Now, from here, it's really easy to finish, because what's the idea? Now we want to see that this is a sphere. So the thing is that the fourth condition that I said before, we know that we have a sphere in the family. We know that we have a solution that is an umbilical sphere in the family. So we're going to assume that doing a translation, if necessary, in this direction, that the axis of symmetry is the one that goes from the north to the south pole. Bear in mind that this is a translation in this direction. In one direction is contained in the totally geodesic hyperplane, so leave invariant this upper hemisphere. And what we're going to do is the following. Place at each point here the sphere that we know that is a solution. So if we go far away, here, close to the boundary, this is not going to touch the equidistant. So we're going to drop the sphere until the sphere makes the same angle that this guy. For sure that we're going to have one point where the sphere is going to make the same angle that this one, right? So now there are two possibilities. Or the boundary, this guy is contained here, or this guy is contained here. Well, or they are equal. One cannot be contained in the other, because if one is contained in the other, if we go up with the one that is lower, I'm going to touch in an interior point, so I'm going to have a contradiction with the maximum principle, or if I lower the other one. So in fact, they have to be the same. This guy has to be a sphere. So a sphere of some radius. It's going to depend on the constant that we fix, the dilation that we have. And if I find it's here. So this proves the first theorem, because one that we know that have to be a totally umbilical sphere, we can compute this function. We have an explicit formula for this hypersurface, so we can explicitly compute this function rho. That it have to be the standard one. That's an easy computation. It's not a hard computation, and it's easy to believe. If you think in a totally umbilical sphere and you think in the hyperbolic Gauss map, it's nothing but you follow the rays. If you place the sphere at the origin, you follow the rays. So the metric, the conformal metric that induced at the conformal infinity is nothing but a dilation of the round sphere. So yeah, I have time. I have a lot of time. So okay, this technique we can use to solve another problem. Say more complicated problem in the sense that here we are dealing with one boundary. Now we are going to assume that we have two boundaries. Suppose that this is the North Pole, and I'm taking the upper hemisphere and a ball centered at the North Pole of some radius. The radius, of course, is less than pi over 2. That is the radius of the equator. And again, I'm going to assume that I have a solution in this region here, so that the scalar curvature of the conformal metric is 1, and now the boundary is minimal. I didn't do anything up to the part where I have that is embedded and the angle is constant. I didn't do anything but to use the representation formula, this representation formula, and the value of the mean curvature. So in this case, if I do all the construction again and everything, what I have is that I can construct a hypersurface with boundary here and here, and the condition on the mean curvature implies that this is a right angle. Okay? So the idea here is to reflect the surface and to construct a properly embedded hypersurface. So I reflect this guy, this part. And then keep on going. So what I have is a properly embedded hypersurface with boundary infinity the north and the south pole. So again, if I use the Alexandrov reflection method, take any geodesic in this totally geodesic, take the hyperplane orthogonal to this guy, so I can keep on going until I get, in this point, this has to be a plane of reflection. This is because the geometry of the hyperbolic space is stronger than the geometry of the Euclidean space. This is easy to see in the following way. If we go until this point, the intersection of this hyperplane, this part of the hyperplane, with the surface have to be compact, because the surface is proper and goes to this point. But until we reach these 2 points here, these 2 points, this part here have to be compact, cannot be non-compact. So we can go with this hyperplane up to this point, and then we can reflect, and it's going to be in the interior domain. If you don't have any interior point touching your hypersurface, you come now in this direction. But then, if you don't find any interior point in this way, you must find an interior point in this way. So in fact, what is happening is that this hyperplane have to be a plane of symmetry. And you can do that for any direction. Therefore, what you prove is that this guy is rotationally symmetric. So if this is rotationally symmetric, this induces a rotational symmetry property for the function rho that we started with. And then we can prove that up to a dilation that we did at the beginning, we can see that this guy, this conformal metric have to be rotationally symmetric. So in both cases, using hyperbolic geometry, we can prove these 2 classification results that Escobar did for scalar curvature. This same problem Escobar did for scalar curvature in the Euclidean space, and with this condition. This condition is very important, because if you change this condition, you allow to have different mean curvature than 0, that say that this angle here are not right angle. So you cannot reflect and to have a nice hypersurface. So you have to be careful with that, because when we did it in the first case, this guy here is going to be invariant. But when you come with this foliation by hyperplane, this new totally geodesic or equidistant is not going to be invariant by that foliation. So you have to be careful. So, okay, I think I finished. Thank you.